Okay, for understanding the concept of work, we're gonna take a look at spring force and the concept of work by the use of the spring force on a body. Now let's see our system now. We have a spring here and then our cart or the body, and the spring is connected to this cart and is showing the undeformed position of the spring, and from their point on the body is pulled, and as a result of that the spring applies a force to the body as kx. However, the body moves to the right. The kx force applied by the spring to the body is to the left. If we think of this in terms of the spring at that instant, let me just try to draw the spring here. There's our spring. At that instant, what happens is the same amount of kx force is also applied to the spring, but now it's in the opposite direction, kx. And the distance covered by the spring at that instant is to the right. So the force and the displacement are in the same direction. So that's why we say during extension or compression, compression would be the same thing if the spring is compressed. So let me just try to do a compressed spring here. Now during the compression, what happens is that the spring will experience a force in this direction, and the amount of force would be again kx, but the spring would be also moving to the left during the compression. Okay, this is the displacement of the spring. X displacement, right? So in terms of that, during extension or compression, the work done by the body on the spring is formulated as kx times dx from x1 to x2. In this case, it's starting from a undeformed position, so you can say that x1 would be equal to 0 for the specific case, but in general, this is from a x1 position to an x2 position, the integration happens. This is our force, which is a function of x. This is our force as a function of x. And this is the displacement, and we are taking the integral of it during this interval of displacement, or the path, as you might say. And this is positive. This is the positive work done on the spring. As a result of that, the spring stores this energy because we are doing a positive work on the spring. However, the work done by the spring on this body is negative. Why? The force applied by the spring on this body is kx, yes, but it's to the left. However, the body moves to the right. So if we take the dot product of these two, we will end up with a negative sign because of the opposite directions of the force and the displacement. So as a result of that, the work done by the spring on the body during extension or compression is a negative work. So here is the idea of that work done by the body is negative. However, the total work done on the spring by the body is positive, and it is calculated by the area underneath this curve. And here is the undeformed section right over here, and this could be calculated at any point of the extension or compression. However, during the release from extension, the work done on the spring is negative. This time the work done on the body is positive. So if you release this body, as the spring is already pulling it, this is extended first, and spring is pulling it by kx at that instant, and the body, as you release it, starts to move in the same direction. Now the work done on the body by the spring is positive during the release. However, during the release, of this extended spring, the force on the spring is in this direction, so this is kx. However, now the motion happens in the opposite direction. Now the motion of the spring, as you release it from the extended condition, the spring tries to bring itself to the undeformed position, and as a result of that, during the release, the work done on the spring by the body becomes negative. Now, I hope this concept is understood clearly. It's an important concept of positive and negative work. And we can take a look at, again, the same type of information that we have talked about, a particle moving on a path, a force is applied to that, so we can calculate the work done on that particle by the projection of this force onto the path, and the projection of that force onto the path is actually equal to Ft times ds, right? Ft is the tangential component of the force, and ds is the path component, or path parameter. Now, F, on the other hand, is equal to ma, right? This is what we know. So, this F vector dot product dr is exactly the same as ma dot product di. So, making use of that information, a dot product dr should be also equal to the components of a vector are a tangential and a normal. Ft is only considered with the tangential part of this acceleration, so this is m times at. Therefore, I can relate this a dot product dr to at times ds, and this is what we remember from our kinematics part of this course. Tangential component of the acceleration times the ds is equal to v dv. This is our third equation applied specifically for NP coordinate resolution of the acceleration, right? You can find this information again from your kinematics lecture notes. And if we make use of this information instead of at times ds in this equation, now we end up with du to be equal to m times v times dv. So we just use this right hand side of the equation in this part. Oops. This part. And then now relate the work done on a particle to m times v times dv. Now if you do the required integration over a certain amount of path, the same integration making use of f vector dot product dr, then this is the projection of ft times ds. Instead of ft, make use of m times at times ds. Instead of at times ds, make use of v times dv, and then as a result of that we get 1 over 2 mv2 squared minus v1 squared, and this says us that the total work done on a particle results in the change of its velocity. We will later call this the kinetic energy. It will result in the change of the kinetic energy, but at the moment you can just define it as the total work done on this particle, which is u, results in the change of velocity from the first condition to the second condition. And as for the unit of work, we use Newton times meter, or in short, joule. J is again a capital letter because of the name of the scientist, that worked in this area of work. We'll continue with the rest in the next video.